So now we have the last two talks of this today, and then this is Diego Urbina, and then now I cannot read the title of your talk. Semiclassical approach to the scattering of non-interacting bosons, two dots, and etc., etc., etc.
Thanks for the nice introduction. And so you can remember this long title, or you can remember probably the keyword, which is boson sampling. And this talk is about boson sampling. So first of all, thanks to the organizers for the invitation. I also get kind of nostalgic because essentially 20 years ago was my first contact with semiclassical method and quantum chaos in a school in Rio. This is where also I have the pleasure to meet most of you, some of you for the first time. And so 20 years later, here we are. Well, this talk is about scattering of bosons, which are non-interacting. So first approach to this is to think boring. We don't have interactions, boring. I want to convince you that this apparently simple setup actually leads to complex dynamics. And these complex dynamics are subject of intense research in several communities right now. And once I try to convince you of that, I want to convince you that you can apply semiclassical methods there at two levels: the level of single particle semiclassics, and at the level of many-body semiclassics, which is semiclassics lifted to Fock space. Okay, so this is what I just told you. Why the scattering of non-interacting bosons gets complex? Well, because bosons are indistinguishable. So you all know about that, but I will briefly introduce indistinguishability. Then how can we drive a quantum classical transition in the sense of a transition from indistinguishability to distinguishability in the manipulating non-interacting scattering of bosons. I will do it for two particles. Then we will put more particles and more channels in our scattering setup. And this will define what is called the boson sampling problem, or the boson sampling problem will be something that happens in this setup, asymptotic setup of many particles and many channels. Then we will try to attack boson sampling using techniques of single particle semiclassics. So the scattering matrix will be written as paths joining incoming channels to outgoing channels, and let it run. Then we will stop, take a break, repeat what we did, the main conclusions of the single particle approach, and then we will jump to the way we kind of address boson sampling from the point of view of many-body semiclassics. Then I will conclude. Okay, so this is something that we all know. Classical particles are distinguishable because I can label them by their position and momentum, and then follow this position and momentum according to the equations of motion. While in the quantum domain, identical particles are indistinguishable. So comes the problem that how to label states of indistinguishable particles, many indistinguishable particles. And then, okay, we have Pauli that will tell you, well, the recipe is straightforward. You take your wave function, you permute the arguments corresponding to two different degrees of freedom, and the wave function gets a plus if the particles are bosons, get a minus if the particles are fermions. And that's it. That's all you need to classify many-body states according to the bosonic or fermionic character of the particles that are involved. And there is some, so of course, identical particles are always identical. That's out of the question. The point is that there is the intuition that, well, an electron that I know is over there and an electron that is over there, they may be in principle indistinguishable, but I can label them by the position and make them distinguishable. So although in this talk, every time I talk about particles, bosons, and fermions, I'm talking about fully indistinguishable particles, you can effectively drive a transition from distinguishability to indistinguishability by playing, for example, with the relative position of your particles. One possibility to do that, famous one, is what happens when you inject two, let's fix it, let's talk about bosons here. I have two bosons represented by these incoming wave packets that hit a beam splitter. I will always take the beam splitter to be 50-50, so equal probability of reflection and the transmission. And you have there, if you think in single particle terms, you have there two processes. One process in which this particle goes straight, and this also. Also the process where this particle gets reflected, and this also. And these two processes, that's the key point. According to the rules of quantum mechanics, they must be added coherently. And because you have unitary matrices representing the scattering process, you may have minuses around. And if you put this setup to work and simply ask yourself, what is the probability for the two particles to live in different branches here, different channels, you will find out that this probability is what you would expect from distinguishable classical particles if the separation, the delay time tau between the incoming wave packets is large. So this is this region and this region. But if you inject it at the same time, quantum indistinguishability effectively kicks in. This minus plays an important role, and you get 0. This profile, this transition that is, you can think as an effective quantum classical or classical quantum transition, is the celebrated Hongo-Mandel effect, which is a hallmark of coherent effects in quantum optics. So this is well understood, widely used in quantum optics effect. What you need for that is, well, a scattering matrix. I don't need it to be 50-50 or something like this, just a scattering matrix, single particle scattering matrix, telling you what each of the individual particles is doing. Then distinguishability comes after when you symmetrize or anti-symmetrize the wave function. And then you have incoming wave packets with certain profile, certain delay. Then if you go and do your homework, you calculate the probability of the two particles to live in different channels. First, you have a contribution that has this form. This is what we will call the classical contribution, when you incoherently add the individual probabilities of the particles to go from there to there. So this is this part, it's just incoherent. It gives a corresponding expression for the Hongo-Mandel profile that is independent on the delay time. If you don't have quantum effects, then the delay time is doing nothing in your calculation. But because we have amplitudes coherently and not probabilities, the probability gets an extra term. This formula is an exact formula for the Hongo-Mandel profile. Depends on a couple of things. First, you have this function here that measures the overlap between the incoming wave packets. So if they are far away from each other, this function f is 0, and you get the classical result. If you inject them exactly at the same time, this function is 1, and something happens here that the peak or the dip of the Hongo-Mandel profile is given by the permanence of the single particle scattering matrix that describes the single particle scattering process. Good. I didn't know what was a permanent before I started with this, so for the few of you that don't know, a permanent is a determinant without minuses. That's a permanent. And we will talk about permanence during this talk. Okay, now, boson sampling refers to the description of this kind of processes when the number of channels is very large and the number of particles is very large. So we want more channels, we want more particles, and what you find there, this is an exact mathematical result you can work out is that the dip of the Hongo-Mandel profile, when you put a lot of particles inside and you ask the question, what is the probability to get them all in different channels, you obtain a profile or some curves, and exactly at 0 delay, when you inject all the particles at the same time, the result is the permanent of a large matrix you construct out of the single particle scattering matrix. There is a rule how to do that. You have to take your sigma and do things with your sigma, repeat rows and columns of sigma, and you construct this matrix. So this is an exact formula for the Hongo-Mandel dip. This review, this tutorial on boson sampling is 5 years old, but still, I fully recommend it if you want to understand all this in more detail. The other thing that happens when you put lots of particles is that, well, you still have a quantum classical transition. If all your particles get injected into the scattering region at very different times, you expect the classical result to emerge. If you start sending them at similar times, then you expect a transition when the quantum mechanics kicks in. And so the exact profile of the Hongo-Mandel in the asymptotic region of large number of channels on particles is a complicated problem. And we partially answer this question, but not fully. It's an interesting open question. Okay. What is the thing with permanents? Why permanents are fancy these days? Well, it turns out that calculating permanents is hard. And by hard, I mean, I'm not an expert in complexity theory, but the people that know about, that classify problems, how to calculate this, and that there is this classification of problems based on the resources you need the resources an algorithm needs to produce the output with the answer of the calculation you want. The calculating permanence of matrices which are not positive defined is one of these hard problems. So it's difficult. This was made very, very explicit in a paper by Aronson and Arkhipov in 2011, where, okay, they say one of the things they exploit there is that calculating permanence of large random matrices actually is hard. And it's hard also for a classical computer, so it's a hard problem. And the boson sampling problem is the problem of sampling a probability distribution given by the outcome of many body scattering of bosons. It's a probability, you can sample it, and sampling this probability is hard. And it's connected with the hardness of calculating permanence. This kind of framework is what we will refer here, and it's known as the boson sampling problem. Well, the thing is, you have linear quantum optics. So you have, they can really produce big scattering setups with a bunch of photons. You inject a bunch of photons. You have beam splitters. You don't need interactions. You don't need nothing. Linear quantum optics is now exquisite technologically, the things you can measure, you can do. So seems like a linear quantum optical device is a kind of quantum computer because it's a device that is calculating permanence for you. And so the moment you mention that, it's not my main motivation here, but the moment you mention that, well, you have a bunch of people trying to build it. And during the last 5 years or something, this order of magnitude dozens of papers, Nature, Science, of experimental groups building a boson sampler. Meaning, what do I need for a boson sampler? I need to inject indistinguishable photons into a linear array of beam splitters and phase shifters. And the thing is that producing these Fock states with large occupations is very, very, very hard. The state of the art is 7-8. Fabricio can correct me if he's around. And to boson sampling to kick and make be very difficult for a classical computer, the estimation is that you need around 12. So we are still not there, and but okay, they are trying. One thing that was mentioned here before is that since boson sampling is a sampling problem, and you want your scattering matrix to be in some sense random, to produce these random matrices is not obvious in the quantum optics setup. So you have to do that to produce random scattering matrix and to actually certify that what you are doing with your quantum computer is boson sampling. So, okay, that's the framework where we are, boson sampling. Now, the question we want to address is what semiclassics says about this problem. So, what we do when we want to do semiclassics for such a problem is to make the scattering problem, I don't call it realistic, but the structure, physical. So now my scattering problem is given by a scattering of particles in a cavity which is chaotic. So you have wave packets representing bosons injected into this cavity, and you see what happens when you do that. Non-interacting particles. So our beam splitter now is this mesoscopic cavity. It supports a large number of open modes. And instead of my photons, I have atoms. For example, a BEC condensate will give you large occupations of incoming states. This will do the job. And so we are happy to know that there is something that our community understands very well, which is that if I have classical chaotic scattering, the single particle scattering matrix samples the space of scattering matrices uniformly. So this we have for granted if we have chaos. So in this setup, then we have a way to prepare the incoming states called atoms. We have a way to generate the single particle randomness that we need because we have chaotic scattering. We have a way to detect, I won't go into that, but cold atom people can tell you where is each of the atoms going after the scattering, can be done. And certification, I won't touch that, but there is a way to certify. So now that we have a system that we can attack semi-classically using techniques that we know. So let's make it precise. What will be the quantum chaos version of boson sampling? So it will be, I have a scattering matrix describing an irregular but a structured cavity where real dynamics takes place in this cavity. And the hard problem of sampling over the probability distribution given by the outputs of a bosonic many-body scattering distribution is translated into the problem or constructing the full distribution of permanence of single particle scattering matrices. This problem, that sounds like naively, okay, we should know a lot about this. Well, this is quite open problem right now. And it's the quantum chaos version of boson sampling, and any progress there, well, will be most welcome. The other thing that we know that will happen if we do things with a physical cavity is that we will have all these mesoscopic effects that we like that much. No? We have relocalization, coherent by scattering in the cavity, and this should be playing a role in our description. Since boson sampling is an asymptotic statement, we need a large number of channels. That's fine. We know how to deal with that. And a large number of particles. That's new, and we have to learn how to do with that. And, well, the good news is that we do have a way to generate random scattering matrices because they fluctuate strongly with the energy, as we know in chaotic scattering. Okay. So that's the problem. Then we started thinking, how do we do semi-classics there? Well, we do our usual business. We write the scattering matrix as a sum over paths connecting the incoming and outgoing channels. Then we need to calculate things like permanence of this matrix modulus square. The precise calculation of this quantity will require to use as an input the very precise single particle scattering matrix, semiclassically. But what we are interested is in averages. We want to approach to understand the distribution of permanence over the ensemble of random matrices. So what we need are averages. Let's start with the first one. The average of the probability, which is related with correlations between scattering matrices at different energies. How many of these things here? Well, you have products of scattering matrix as many as particles you have. So when the particle number is very large, you have a large product of sums over paths. And then you have to sum over permutations because you need to include the correct symmetry of the wave function. Sorry. And there are people here that know very well about this business. The way we address this kind of calculations semiclassically is looking for correlations on actions, on the set of actions involved in the single particle scattering matrices here. So you have to go look for these action correlations and then do the whole combinatorics because of the sum over permutation. So this is hard. This is a difficult thing to do. This is how it looks. Each line here represents one particle going from some initial channel to some final channel, and the conjugate, the red one, because you always have actions and minus actions because you are conjugating your scattering amplitude. So this is the most trivial thing. Every particle goes from initial to final, and you pair it with the conjugate of the same trajectory. This is the brute diagonal approximation. Then you start getting effects, some of them known to us. For example, this is a particle. These are two paths belonging to the same particle, one having a crossing, the other don't having a crossing. So this is a single particle quantum correction to the diagonal approximation. Then you have also two particle effects, like this one. This is kind of Hongo-Mandel thing. The particles are doing, you are looking for the interference between this process and this process just between these two pair of particles, and so on. And so you have really a monster thing, a huge number of these diagrams to construct. You need to classify them. You need to evaluate them. For each diagram, there is associated a contribution that you can evaluate, some integral. And then you want to simplify all this monster. Well, this is very hard, so don't try that alone. But, well, we do have an advantage, which is that we have our local quantum computer, which is Jack. Some of you know Jack, real master dealing with action correlations and combinatorics. You need the two things actually to deal with this problem. It's heavy. And, well, Jack managed to go on or complete this calculation. And I'm showing you just to show you that out of this huge, very, very complicated thing, you end up with very simple compact results. This is the full average of the probability to inject your bosons in certain set of channels and get them out. It's not the Hongo-Mandel, it's just the probability of a many-body process. That's it. And it's really of the number of channels, capital N, and the number of particles, small n. And it's a very simple combinatorial expression. This function here accounts for weak localization effects. So you can forget it for the moment right now. You can say that it's just one. And the result is this simply combinatorial object that I guess some of you will recognize immediately and give something actually intuitive. You have a many-body state incoming. You take your system, put your many-body inside, shake it, because we are averaging over the ensemble of a single particle scattering matrix. Well, the probability should be homogeneous. But homogeneous where? Homogeneous in the space, in the bosonic space where you are. And this gives you exactly the uniform probability distribution in the output channels, in the many-body output channels of your system. So this makes sense, but I have to confess, we first did the calculation, and then we realized this is that the results makes this lot of sense. Now, if you want to take the square of this probability and calculate the average, and you are able to do it, you probably will be famous because there are a bunch of conjectures, some problem conjectures about the behavior of the moments of this probability over the unitary group. And so there are few results on permanence using random matrix theory or semiclassics, universal averages of permanence and moments of permanence and things like that. I know one paper from Jan Fyodorov, and that's it. Now, the other thing you can do is to see this quantum classical transition. This was the dip of the Hongo mantle. All the particles enter at the same time, and you see the probability to see them exiting in certain many-body configuration. For the Hongo mantle profile itself, what you do the calculation, and what you find is that I'm doing this for 2 particles now, but the number of channels to infinity. What I'm doing here, I'm showing you here, is this blue curve is the result of the normal Hongo mantle effect, which in this case has a Gaussian profile. And is valid when the dwell time of the cavity is very small. So if the dwell time is very small, then think that your cavity looks like a beam splitter, and that's it. There is nothing happening inside. But if you start increasing the dwell time of your cavity, this Hongo mantle profile gets these exponential tails that eventually dominate, and it becomes universal. So if you have chaotic single particle scattering, the Hongo mantle profile is universal and is exponential instead of Gaussian. This is one of the things you can do with this machinery of single particle semiclassics for the Hongo mantle. So let's, I want to make a stop here and tell you again what have we done with single particle semiclassics for Hongo mantle. So the people have noticed that scattering of non-interacting bosons displays complexity. What do I mean by complexity? That characterizing the many body scattering probability is very hard. This is what I mean by complexity. So from one of the reasons that you can think why this problem displays complexity is that sampling over the probability of outcomes of this many body scattering requires the calculation of permanence, which are hard to calculate. Now, if we address this from the point of view of single particle quantum chaos, then the version of boson sampling is that we need to calculate the distribution of permanence over the ensemble of random matrices, random scattering matrices. This is a very hard problem. This will be the random matrix theory point of view. And from the semiclassics, in terms of path interference that we all love and like, it means to compute extremely high order diagrams involving action correlations of many particles and many channels and lots of combinatorics. So this is what we did in this paper. And now what we want is, one of the reasons why boson sampling is so hard is that you have these sum over permutations, right? You have these sum over permutations because you have bosons. So if you are able to lift semiclassics into Fock space, well, you still have bosons, but they are hidden there in a very, very efficient way, simply in the algebra of your creation and annihilation operators. So it seems like at least part of the problem of the complexity will be lifted or moved somewhere else if we are able to formulate everything in Fock space. So this is what I want to do now. This is something that everyone knows, but I just, for completeness and fixing notation, I want to go through. Now, if I want to formulate this using many body semiclassics in Fock space, then I need to formulate this in terms of second quantization. What is the second quantization formulation of this problem? Well, I have an incoming state, which, how do I construct this incoming state? I put a bunch of particles in the first channel, a bunch of particles in the second, a bunch on the third. This is what these creation operators are doing. But I do that in the incoming state. So these B operators I have here are creating or destroying particles in the incoming mode. How do I see what goes out? Well, I have to construct states where you populate outgoing states. And this we will do with these D operators. That's standard, formal. What is the relation between the D and B operators? Well, the single particle scattering matrix. This we all know. So now you can have a glimpse why this thing is so awfully complicated. Imagine that you want to calculate the overlap, the probability of getting certain out configuration when you put certain in configuration. Well, you have to do this, right? Doesn't look that bad. What this means, I have to take one of these monsters, I have to overlap with one of these monsters, and I have to do this transformation of the operators inside these powers. So you can see that this gets very big, very quick. And that's an intuitive reason why this problem turns out to be so complicated. And, but okay, the formulation is like that, no big deal. You can, before going into the semi-classics for Fock states, which is what we are interested, you may pose the following question. Okay, why do you work with these complicated Fock states? They behave so nasty under the scattering transformation and all that. Why don't you try another type of state? So let's try another one. You can try to do the same, but with incoming and outgoing many-body bosonic coherent states. How does it work? There is an operator, the D operator, that allows you to create, construct a many-body bosonic state in the incoming mode of this form. This is a generalization of the coherent states we all know and love for the harmonic oscillator. Well, you look the incoming creation and annihilation operators here. You can you can construct your out state. You can ask the same question. Well, you have this complicated scattering in between, but I want to know what is the probability to inject a many-body coherent state, certain incoming configuration, and get certain outgoing configuration. What happens is that coherent states are kind of very classical in the sense that they transform trivially under the scattering. So the outgoing ones are given by the application of the sigma on the incoming ones. Just like it's very simple. And then if you go do your homework and calculate the probability, not with Fock state, but with coherent state, you get this very simple result. What does it mean? These are classical fields. You have your scattering region. You inject a laser in the different modes with certain amplitude and certain phase. You ask what is the probability to get certain amplitudes and certain phases over there. Well, you simply apply the scattering matrix to the incoming field and put it in an exponential like that, and that's it. So this is not hard at all. There is no mystery in calculating many-body scattering probabilities and amplitudes for coherent states. Boson sampling is about Fock states. That's the thing. And people actually explored this idea, and what they found out is that you can really map the hardness, the hardness of boson sampling to the fact that the Wigner representation of Fock states is non-positive, has negative regions. And you can map this into the hardness of boson sampling. And since the Wigner representation of coherent states is purely classical and positive, then you don't have this problem. So this already should give us, especially to this community that we talk about path interference all the time, that the hardness of boson sampling has to do with interference. That's what's going on. Massive interference. Okay, so now I will just show you the results of taking boson sampling and the semi-classics of boson sampling into Fock states. Fock space. I will just tell you the results because I think it's intuitively quite clear. So you want to go from real space to Fock space. Turns out that there are special operators in Fock space called quadrature operators, familiar for people in quantum optics, that kind of lift into the many-body space the standard position and momentum operators for single particle systems. So you have incoming quadratures and outgoing quadratures. The small are incoming, the big are outgoing. You can construct them because they are based on the incoming and outgoing field operators. So you know how to construct these objects. Then they have an immediate classical limit. They go into phase space coordinates, real and imaginary part of your incoming and outgoing fields. 5 or 10? 5. Okay. Now comes the interesting part. Turns out that if you don't have interactions, then many-body scattering is nothing but a canonical transformation. It's a linear canonical transformation that takes linearly the incoming canonical variables into operators into the outgoing canonical operators. This can be shown. So then, we know semiclassically what does amplitude, quantum mechanical amplitude means. The quantum mechanical overlap between, for example, a Q state in the incoming basis and a Q state in the outgoing basis is, this is a unitary transformation performing a change of basis. So I can express it in the well-known WKB form through the generating function of the classical transformation going from a small q to big Q. That's the key point here. If you remember this from this talk, I'm very happy. These kind of overlaps are represented by canonical transformations, and they are represented by generating functions. Since this canonical transformation is linear, the generating function is trivial, and very important, it admits one unique solution for the problem of finding, if I give you initial and final Q, there is only one function, one branch, it's a function with only one branch doing the job. This can be shown because it's linear. So I don't have a sum over branches, nothing here. And again, this is boson sampling. I'm going from incoming to outgoing, but this boson sampling of in a representation when things are simply trivial. So it's not hard. And again, the origin of the fact that this is easy is essentially because I don't have interference. I don't have different branches for my generating function. So what happens if you go to Fock states? You go to Fock states, the problem is different. Now you want to go from a set of intensities, initial and final, and the corresponding phases. This means this problem here. I give you a bunch of initial intensities and phases, and you linearly map it into a bunch of final intensities and phases. But now you want to, your problem is defined by, I give you the intensities initial and final alone. This problem is massively multi-value. So the generating function doing that has many, many solutions. And it's because you have all these solutions that this amplitude is difficult to calculate because you have massive interference going on there. So yeah, the complexity of boson sampling then is due to the existence of all these branches. Now I finally came to the results. If I want to put this idea to work, then let's try first a case where I have an analytical solution. Turns out that the case of 2 incoming modes and 2 outgoing modes with arbitrary large number of particles admits the construction of the generating function can be done fully and analytically. And this is what I'm showing here. You have the transition probability between this incoming state and this outgoing state as a function of the number of particles in the first outgoing mode is here. For 4 particles here, you see a bunch of points. The circles are quantum mechanical exact calculations. So it goes from there to there to there to there to there. Why do you get 0 here? Well, this is Hongo-Mandel. You have 0 probability to get them in certain configurations, let's say. The crosses are the results of the asymptotic semiclassical analysis I just told you. So for many body semiclassics expects to work better the larger the number of particles. So for 4 particles, it looks like that, 6 like that, 10, 30, and 100. And there you see that semiclassics catches everything, including the zeros that are here that interference effects. Classical mechanics will give you something like around here. Now semiclassics give you the whole pattern. And so as I mentioned, the origin of complexity here is the existence of many branches of the generating function. So just to finish, what I'm showing you here is how you try to actually find the branches. What we do is, this problem is known in optics. It's called the phase estimation problem. So I give you a field and the Fourier transform. And then I give you only the intensities of the field and of the Fourier transform. And I ask you, find the phases. This is a known problem in classical optics, and there are algorithms to solve it. The algorithms are iterative, and what I'm showing you here is in color how long it takes to converge to a solution of the phase estimation problem. You don't need to, let's say, this represents the basis of convergence of the solutions of the boundary problem that determines the transition probabilities. And yeah, I like it because, as expected, it will get a fractal equation. Okay, so that's it. Many body scattering of non-interacting bosons is complex because of massive interference in real space, because of the multivaluedness of the associated classical problem, which is a phase estimation problem, and because of the difficulty of calculating the distribution of permanence in RMT. And with this, sorry for taking too long, and thanks for the attention.
Where is the value of the